The Johnstone Supply Company, Cafferty Group, located in Nebraska, Iowa, Kansas, and Colorado, presents Understanding Inverter Operation. Inverter use in the HVAC industry has grown tremendously in the past few years. This technology is here to stay. The better we understand it, the easier it is to service. Here is an example of an inverter board. We are going to go through the components that make up an inverter. We will cover not only what the components are in the system, but what they do, how they do it, and why. Let's look at a basic inverter board layout. We start with incoming AC power. That power is converted into a DC signal through a diode stack. It then is routed through a smoothing circuit, which consists of a reactor and smoothing capacitors. From there, the DC power enters the inverter section, which is IGBTs or insulated gate bipolar transistors, and they convert the DC voltage into a three-phase AC variable frequency, variable voltage to operate the compressor. Here's an example of an inverter board schematic. The blue lines represent 208, 230 volt single-phase AC power. The red lines represent the DC power after it's been changed in the diode stack. The purple lines represent the simulated three-phase AC power to run the compressor. The green lines are the system ground. The 208, 230 volt AC power enters the outdoor unit on L1 and L2. Sometimes the AC power entering the outdoor unit contains noise that is picked up through the transmission lines on its trip from the power generating station. To ensure the system runs at its maximum efficiency, the first thing that the power sees is a noise filter section, which removes white noise and harmonics from the incoming power. The cleaner the incoming power, the more efficiently the system will operate. This is accomplished by the use of a common mode choke coil. Simply put, depending on the size of the choke coil, there are two or more windings. The windings on a coil are wrapped in a way that they create a magnetic field. That magnetic field restricts an increase in current. The current in a group of lines moves in the same direction. So the combined magnetic flux creates an opposing field to block noise, thus removing the white noise and harmonics typically found in incoming power. Once the incoming power has been cleaned up by the noise filter, the power arrives at the converter circuit or diode stack. The converter circuit uses a group of diodes to change the state of the incoming power from AC to DC. A diode is an electronic device that allows electricity to flow in one direction and blocks the flow in the other. So without a degree in advanced quantum mechanics, for lack of a better term, we'll say it works as an electrical check valve. This is how we change AC power to DC power. Notice the schematic diagram on the right side in the center that shows an arrow with a line at the point of it. The arrow shows the direction of the power flow. Power always flows from anode to cathode, which is from positive to negative. Power is blocked from cathode to anode. When AC power is changed to DC power in the diode, there is an increase in that voltage. The increase is a multiplier of 1.414. So whatever your incoming AC power is, multiply by 1.414, and that's what your DC power should be. For instance, if your AC voltage coming in is 208, your DC voltage would be around 293. If your AC voltage coming in is 245, your DC voltage should be about 345. Next, let's discuss the reactor. Depending on the manufacturer and the type of system you're working on, the reactor can be found on some systems in the AC incoming power and on others in the DC power after it has left the diode stack in the smoothing circuit. In this schematic, the reactor is shown in the AC side. The reactor resembles a transformer, but the incoming and the outgoing voltage are the same. When the reactor is on the AC side, it reduces inrush current, harmonics, and improves the power factor. When the reactor is located between the diode stack and the smoothing capacitors, it helps to stabilize the inverter and improve the power factor. When the reactor is installed on the outlet side of the inverter, it lowers line, noise, and pulse voltage from the inverter. To test the reactor, use an ohm meter. Across the windings, you should have 0 ohms resistance or full continuity. If you get an open circuit, the reactor is faulty. A defective reactor in the incoming AC power circuit can damage the outdoor and the indoor control board. So what is a reactor used for? It improves inverter system reliability, reduces inverter system downtime, improves the true power factor, allowing the inverter to run more efficiently, eliminates inverter nuisance tripping, reduces incoming current harmonics, extends motor life, reduces motor peak voltage, reduces motor temperature, reduces motor noise. Next in line for the power is the smoothing circuit. When the system changes the incoming AC power to DC power, because it alternates 60 times a second, there is a pulse in the DC voltage. The smoothing circuit is a series of smoothing capacitors that store voltage and discharge when there is a lull in the DC voltage, thus creating a smoother voltage entering the inverter section. Now that the incoming power has been converted to DC, cleaned up, and smoothed out, it's time to convert it to a 3-phase AC to operate our compressor. This is accomplished in the inverter circuit. The inverter circuit, sometimes referred to as an intelligent power module, converts the DC power to a simulated 3-phase AC power to operate the compressor. It creates variable voltage at a variable frequency to control the speed and capacity of the compressor, typically giving the compressor the ability to run between 20 and 125 Hz, rather than just 60 Hz at 3,350 RPM. The inverter circuit utilizes 6 IGBTs or insulated gate bipolar transistors. Depending on the configuration and the manufacturer, this could consist of 6 individual IGBTs or triacs, or one large chip. The IGBT is a 3-terminal electronic component. The collector terminal is the incoming DC voltage. The emitter terminal is the exiting power going to the compressor. And the gate terminal is the trigger. The more voltage that is applied to the gate terminal, the more voltage is sent out to the compressor on the emitter terminal. Since the compressor is 3-phase, there are 6 IGBTs, 3 of them pulsing in a positive sine wave shape, 3 of them pulsing in a negative sine wave shape. This is an example of a 5-pulse modified AC sine wave made from DC. This is what the sine wave actually looks like on an oscilloscope. You can see the 6 IGBTs on the inverter board. The simulated AC power travels to the compressor on terminal designations U, V, and W. Polarity is important on the 3 compressor terminals, just like any other 3-phase compressor. If the U, V, and W terminals are wired out of phase, the compressor could run backwards. Because there are 6 IGBTs, this is a 6-step rotation pattern of the magnetic field. Each magnetic pulse rotates the compressor by 60 degrees. This diagram shows the compressor rotation. It also shows which terminals are energized to create the magnetic field to rotate the compressor. Thank you for joining us on this journey to better understand inverter operation. For more information, please contact your local Johnstone Supply Company, Cafferty Group office.